Hi everyone, so welcome to this video on grid-based dynamic programming. So in this section we will discuss some common grid problems that generally come in coding competitions and they are based upon DP. Okay, so in grid-based problems you are given generally a 2D matrix and you have to do some kind of an optimization. Okay, so one of the variant that is very common is you have to find out minimum or a maximum cost path in a 2D grid. Okay, so you will be given a grid like this and you might be asked, okay, tell me what is the path from, let's say, this position to this particular position, and what is the minimum cost of the path that is possible. That is one way, and it can be possible that some of the cells in the grid are blocked, and then you have to find out what is the maximum or the minimum cost path. And another is you have to find the number of ways to reach a particular position given a starting point in a 2D grid. Maybe what is the number of ways in which you can reach this particular position. That is another possible type of problem that can come. Okay, so throughout this section we will see some common variations of these kind of problems. Okay, so let's start with the first type of a problem that is pretty simple and easy to solve. Okay, so suppose you are given a 2D grid like this, and let's say this is called a cost matrix, where each cell in the cost matrix ij denotes what is the cost of traversing that cell. Okay, so if this cell has a value 5, that means you have to spend 5 units to cross this cell. Okay, to cross this particular cell. And the question is, given the cost at each particular cell in the array, you have to find out the minimum possible cost to reach any particular cell starting from, let's say, this cell that is 0 0. Okay, so you have to tell what is the cost of, maybe from going from this point till this point, what is the minimum cost path that is possible to um, reach the destination. Let's call this as x comma y, or let's say this is equal to r minus 1 c minus 1, where this has r number of rows and c number of columns. Okay, so this is what we are interested in finding out. So there are multiple ways you can make a recursive solution. Okay, but as you know, a recursive solution will have computation of overlapping subproblems again and again, and that's going to be a inefficient solution. So that's why we are going to directly look at a DP based solution. Okay, what you can do is, at any given cell, okay, let's say this is the particular cell. Okay, we can look this problem in using both top down and bottom up DP. Okay, so let's say you are standing at this particular point and you are interested in finding out what is the cost to reach this particular cell. Okay, so I will assume if I have reached this particular point, I have already covered all the cells um, that are lying behind this cell. Okay, for example, I will assume that all these cells that I am making in the white grid, they have been covered by me if I'm standing at this particular cell. Okay, so suppose now I want to reach this particular cell, and I am interested in finding out what is the cost possible. Okay, now at any given cell x comma y, you can enter this cell only from two directions. Okay, you can enter from top, and it's also given in the question the moves that you can take are right and down. Okay, from any given cell you can only move in two directions. So from this cell you can go right or you can go down. So if you are entering this cell, so either you are entering this cell from top or you are entering this cell from left. So that would mean, if we are doing some kind of a bottom up DP, that means we already know what is the cost to reach this particular cell, and we also know what is the cost to reach this particular cell, and you are interested in finding out what is the minimum cost to reach this particular cell. So that is very simple, that is going to be the minimum of these two. So dp of x comma y will be minimum of dp of x minus 1 y comma dp of x comma y minus 1, that is the top cell, plus the whatever cost you will spend at this particular cell x comma y. So that's it, that's going to be the recurrence, and you can compute this for all values of x comma y, and this can be solved in order of n square time. Okay, so let me give you one example also. Let's say this is a small grid, and let's say this is 1 5 2 7 8 1 1 1 and let's say 3. Okay, so I'm interested in finding out what is the minimum cost path from this particular cell to this particular cell. So what I will do, I will build a cost matrix. Okay, so in cost matrix I will fill out these values in a bottom up manner. So I know what is the cost at this cell, it is 1. What is the cost at this particular cell? Okay, so these two are going to be special cases, the first row and the first column, because in the first row you have to come from the left, and in the first column there is no other option to come except you have to come from the right. So cost to reach this cell would be 6, and the cost to reach this cell would be 8. So I'm just adding taking a sum of previous costs. Okay, similarly here the cost would be 8, and here the cost would be 8 plus 8 16. Okay, and at this particular cell you can take the minimum of top and the left, that is 6 plus 1, this is going to be 7, and at this cell this is going to be 7 and 8, minimum is 7 plus 1 8, and at this cell it's going to be 7 and 16, minimum is 7 plus 1, that's going to be 8, and at this cell you have uh, 8 and 8, minimum is 8, and you can say the minimum cost is 11. So that means either you come from the top or you come from the left, both the paths will have a minimum cost. So one of the paths that is going to have a minimum cost is, you can also mark in which direction. Okay, so this is one path. Okay, and this is another path. Okay, 1 5 1 1 and 3, and 1 5 1 1 and 3. Okay, so these are the two paths that we are able to figure out from this. Okay, so at each cell you can also store the direction from where we are taking the minimum. Okay, so for example, for this cell the cost was 8 because we came from left, so you can store a arrow or a variable that denotes in which, from which direction we are coming to this particular cell, and that will help you to reproduce the path that led to this minimum cost solution. Okay, so the code is going to be very simple. Okay, we are just going to implement this recurrence, and I will not write the entire code, I will just show you what I have written, and it's actually very simple. Okay, so this is the function to find out the minimum cost. So I'm just putting a loop from 0 to r minus 1, and a loop for columns from 0 to c minus 1, and if I see, if I'm standing at the first cell, this cost is same as cost of 0 0, and if I am in the first row, then I see what is the cost at the previous column in the same row, that this is j minus 1, this is 0 comma j, and I say okay, add the cost of this cell to this, so I get this answer. And similarly for the first column I have a different condition, so I add what is the cost in the previous cell of the same column, and I add the current cost. Otherwise we simply implement this particular recurrence that is equal to this. Okay, okay, so this is how you can actually approach a minimum cost problem, and in the next video we will see the other variation, when you want to find the number of paths. Okay, hi everyone, in this video we'll discuss another variant of grid based DP, where you actually are interested in finding out number of ways to reach a cell in a 2D grid. So it's given that you are standing at a, let's say, given cell 0 0, and you want to reach a particular cell, let's say the last cell in the grid or any other cell in the grid, and you want to know how many ways you can reach this particular cell. Okay, so as you can see, this will be counted as one way, this will be counted as another way. So you want to find out how many ways there are if the animal is a rat. Okay, so animal can move one step right and one step down. And in the second case, it's given it's an elephant, and an elephant can move more than one step. Okay, like in a game of chess, elephant can take a single step and reach this point, it can take a single step and reach this point. Okay, and this will be counted as one way. But suppose if the elephant moves like this, then goes like this will be counted as another way, because it's taking more number of steps to cover the same path. Okay, so that is the second variant. Okay, so we will discuss the solution to both of these problems. Okay, let's first discuss the rat version. Okay, so rat version is pretty simple. Okay, and this can be done again using recursion or top down DP or bottom up DP, but I will just take up the bottom up DP approach because it's the most simplest to understand. Okay, so what we need to do is, suppose you have a grid like this, 3 cross 4, and you also know the rat is currently standing at this position, so there is one way to stand at this particular position. And then you will start filling this grid in a top to in this manner. Okay, in a bottom up manner. So what you will do, you will see, okay, what is the number of ways to reach the next cell. Okay, so at the next cell you only know the rat can come only from the left, so this will be also 1. At this cell you also know the rat can come only from the left, so this will be 1. At this cell you know rat can come only from the left, it will be 1. Similarly, the first column will have only one way, because this is the only way in which rat can go. For the remaining cells that are there at any given cell, let's say x comma y, let me denote this as like this, dp of x comma y. So dp of x comma y will be actually sum of two values, because here you have an option, a rat can come from the top or it can come from the left. So it will be nothing but dp of x minus 1 y plus dp of x comma y minus 1. Okay, so this answer will be 2. Similarly, this answer would be 1 plus 2 3, this will be 1 plus 3, that is 4. Similarly, it will be 3, this will be 6, this would be 10, and this would be 4, this would be 10, and this would be 20. So the final answer is going to be 20. So this you can just compute for all the cells, and the complexity would be order of n square. So let us discuss, is there any other way to compute? Okay, so if you do it using recursion, okay, in that case the complexity would be exponential, because of overlapping subproblems that you are not considering. Okay, so in recursively if you do, it would be 2 raised to the power n. Using dp if you do, it would be order of n square. And in other ways you can also solve this problem mathematically by using p and c. Okay, so what I'm trying to say is, if you want to, let's say, traverse 4 cells right and 4 cells down, you actually need 3 steps. Okay, you actually need 3 steps in the right, and you also need 3 steps in the down. Okay, and you can permute these steps in any order. For example, if I say, okay, first I will take 3 steps towards right, and then I will take 3 steps towards down, I will reach this cell. Okay, or I can say, okay, no, I will take 2 steps right, then I will take 1 step down, I will take 1 step right, and I will take 2 steps down. Okay, so what you're doing, you're just arranging right and down moves in any given order. Okay, so you want to find out all possible permutations of right and down that you can make. Okay, so number of right moves that you want to make is actually n minus 1, and number of down moves you want to make is m minus 1. And if you want to arrange this, so total number of arrangements will be m minus 1 plus n minus 1 factorial upon all the right moves are identical and all the down moves are identical, so upon m minus 1 factorial and n minus 1 factorial. Okay, so if I just put these values as 4 and 3, okay, m is also 4 and n is also 3, so this is going to be 4 minus 3, sorry, n is also 4, so 4 and 4, so it's going to be 6 factorial divided by 3 factorial and 3 factorial. Okay, so let's see what this is going to be. So 3 factorial cancels with this, so I get 4 5 6 upon 3 factorial, so this goes and I will get the answer as 20. So you can see this answer is also 20. So that would mean I can also solve this problem in order n time if I just use this particular formula. So this is the formula to get the number of ways, but you cannot apply this formula if some of the cells are blocked. Okay, so if some of the cells are blocked, then you can say, okay, this recurrence will hold. Otherwise, if a cell is blocked, you can just say the number of ways to reach that cell is 0 if cell is blocked. Okay, so that you can check. Okay, so that will be given in the question if the cell is blocked or not. Okay, so this is the rat version. So we have discussed three approaches. One is the recursive one. So in the recursive one, you will actually make two calls. So if you want to reach this particular cell, f of x comma y, you will say it is nothing but sum of previous two, f of x minus 1 comma y plus f of x comma y minus 1, and this will actually take a exponential time. Okay, so recursive, dp, and the formula based approach. Okay, let's now discuss the second version, that is the elephant version. Okay, so what's different in elephant version is, for a same path, there are multiple possible ways. Okay, so there are multiple possible ways for a same path. So suppose there is an elephant standing at this point. So elephants will say, okay, I will just go straight and then I will go down. So this is one way. But let's say there is a lazy elephant. It says, no, I will go one step, I will take some rest, I will go two steps, I will take some rest, I will go one step, I will take some rest, and then maybe I will go two steps, take some rest, and go there. So this is another path. Okay, and clearly there are at least two ways to cover this same particular path, but there are more as well. Okay, so how do we now think of this problem? Okay, so let us again try to break this down, and I will just uh, again take the bottom up approach. Okay, because that's the easiest approach in grid based problems. So let's try to think. Okay, so we have to think in how many ways we can reach a given cell. Okay, that's what we need to figure out. Suppose you're standing at this point, you have only one way, but now let's say you go to this particular point, how many ways you can come? Okay, so clearly there is one way because you can come from directly here. Okay, now let's say you go to the next cell, what and how many ways you can reach this particular cell? So clearly you can take a jump directly to this cell, so that will contribute one way. You can also come via this cell, so that means there are 1 plus 1 2 ways. Okay, so how many ways to reach this particular cell? Can you make a guess now? So clearly it's going to be, you can take a direct jump one way, you can come via this cell one way, you can come via this cell two ways. So 2 plus 1 plus 1, that is 4 ways. Okay, so why 4? Because if you clearly see, okay, to reach this particular cell you have two different ways. So you take a jump of 2 and then you take a jump of 1, or if you you do 1 1 1, that is one way, or that you can also do like this. In order to reach the fourth cell, you can take a direct jump, that is you take three jumps directly, you reach the fourth cell. Or you can say, I will take one step and then I will take two steps, so that will make you to take three steps. So you have four different ways. Okay, so clearly for this you will have 4 plus 2 plus 1 plus 1, 6 7 and 8. Okay, similarly here you will have 1, and here you will have 1 and 1 2. At this cell you can come from top and you can also come from left, so this will be 2. At this cell you can come from the top in two ways, you can come from the left in two ways, and you can also come from this cell, so it will be 5. So this will be 5 plus 4 9 plus 2 11 and 1 12. It will be 12 plus 8 20 plus 5 25 and 2 27 and 1 28. Okay, so similarly you can just fill up all the cells. So what I'm saying is, dp of x comma y at any given cell, what you need to do, you need to take a sum along the rows and the columns. So dp of, let's say, sum k comma y, change the rows. Okay, so k goes from, let's say, 1 to x minus 1 plus dp of x comma k, where k goes from, oh sorry, it should be from 0 to y minus 1. Okay, so at every step you have to take the sum. Okay, so for this cell you will just take a sum of this column and this particular row. So it's going to be 1 plus 2 plus 2, that is going to be 5. Okay, for this cell you take the sum of this column, that is 12 plus 5 17 to 19 20 and 8 this is. Okay, so that's what I have written in the recurrence. Okay, so what would be the complexity now? So the complexity of this solution would be, you need to compute for all xy. That means this loop will run n square times, and for every cell you need to iterate over row and a column, that takes n times, so it's going to be order of n cube. Okay, so again, this is actually a 2D version of the ladder problem that we have done in 1D DP. And one change is there, instead of having a jump of k, we can, the k value is variable. Okay, so that's what this problem is. Okay, so I hope you got an idea, and regarding the implementation, they are pretty easy, and in most of the DP problems the implementation is really very easy. The most challenging part is to come up with the recurrence, and if you find out the recurrence, the implementation is just a cakewalk. Okay, so thanks a lot, see you guys in the next video now.
Hello friends, in this video we are going to discuss one problem from Code Chef. The name of the problem is Robot and the Paths. So in this problem, let us first go through what the problem says. So you are given a robot which can move in a rectangular grid of size m cross n. So the grid has m number of rows and n number of columns. And initially the robot is positioned at the first cell of the grid, which is 1 comma 1. So this cell is 1 comma 1 at robot is standing at this position. Right? So robot is at this position, and it is also given robot can move only in two directions. It can move in east and it can move in south. The robot can go to this cell and the robot can go to this cell as well. So, and it is also given there are some random obstacles in the grid through which the robot cannot pass. Right? So we are given the coordinates of the blocked cells. So in the next p lines we are given what all cells are blocked, and we have to count the total number of paths the robot can take to reach the destination. Suppose the following cells are blocked, then the robot can take this path, or it can take this path, or it can take some path like these, right? So in the following example, you can see there are multiple paths to reach the destination, such that we have to avoid all the obstacles. Since the answer can be large, we have to print our answer mod this, right? So let us see what is the sample input. In the sample input, we are given three things. The first thing is m, the number of rows, the number of columns, and p. So here it denotes the number of cells which are blocked. So p is the number of cells that the current cell is blocked. In the next p lines we are given what all cells are blocked. So in this grid it is given that 3 comma 3 is blocked, so this cell is blocked, and 3 comma 1 is blocked, this cell is blocked, and we are given what is the dimension of the grid, right? So let us see how we can solve this problem. So let us make one grid and let us try to build our solution. Suppose this cell is blocked, this cell is blocked, these all cells are blocked, let's say. So suppose this is the cell I want to reach. This is the cell I want to reach. So let's say this cell is I comma j. Now to enter this cell, I know that there are only two options through which I can enter this cell. One option is this, the other option is this. So I can say answer of ij, let us make one array which stores what is the number of ways to reach a particular cell. Suppose the array already stores what is the number of ways to reach this cell. So this is going to be answer of I minus 1 j plus the number of ways to reach from the left. Suppose to reach this cell there are 4 ways, and suppose to reach this cell there are total of 5 ways. So to reach this cell I can say there are total of 9 ways possible. This is a very simple recurrence which we can form. So this is going to be answer of I comma j minus 1. This is the case when both of the cells are not blocked. If any one of this cell is blocked, suppose this cell is blocked, so what is this coordinate? This coordinate is nothing but I minus 1 comma j. So this value is going to be 0 because a particular cell is blocked, so there is no way of reaching this. Suppose this cell is blocked, so this answer is going to be 0. And what we are going to do, we are going to construct one array and we are going to compute the number of ways to reach the destination. Suppose none of the cells is blocked, suppose there is no obstacle, so I can say to at 1 comma 1 I have only one way to reach this cell. I can come from here, it is again one way. To reach this cell it is one way, to reach this cell it is again one way. Similarly, one way, one way, one way. So this forms our base case. If we are standing in the first row or in the first column, the number of ways to reach that coordinate in that row, first row or in the first column is going to be 1. But suppose if one of the cells is blocked, I see this cell is blocked, so this answer is going to be 1, this answer is going to be 1, this answer is going to be 0, and onwards all answers are going to be 0 because we cannot move after crossing this cell. We cannot go like this, right? So all the answers after the blocked cell are going to be 0. And similarly for this cell I can say the answer is going to be 2. The number of ways from coming from left and from the top, this is going to be 2, this is going to be 3, this is going to be 4, and similarly it is going to be 3, this is going to be 6, and this is going to be 10, and so on, right? This will continue. So we will use 2 for loops to compute answer of ij, or I can say dp of ij. So this problem can be solved using dynamic programming because we are computing the answer for every ij once, and this we are doing for all the states, right? So it becomes a problem of two-dimensional dp. Now let us try to write the code for this problem. So I have constructed one dp array. I have already initialized it with 0, and all those cells which are blocked, which are given as blocked in the question, I have marked those cells with -1, right? I have marked all those cells with -1. Now I'm going to write one function which computes the number of ways to reach the destination. So I get the current row and the total rows and the total columns, right? So starting position, I know I'm standing at 0 0, so I'm assuming the indexing from 0 0, and one of the base cases, if we are at origin and we see that the dp array contains -1, so it means we cannot move forward. So there are 0 ways. If the starting cell is blocked, then we say that there are 0 ways. Suppose this is the array and suppose this cell is blocked, 0 0 is blocked, then we say that the total ways is 0. Otherwise, let us compute the number of ways for first row. So for the first row I can say for int j equal to 0, I will iterate over all the columns. J is less than the number of columns I have, j plus plus. So dp of, if I found that a particular cell is blocked, if dp of 0 comma j is equal to -1, right? Then I will break. I do not need to go forward in that row. Otherwise, I can say dp of 0 and j is going to be 1. So let us say what it means. If I say that this is the row and I say that this cell is blocked, so the answer for these two positions is going to be 1. Onwards, if this cell is blocked, so I do not need to compute the answer for these. So there are automatically these number of ways are going to be 0 because the dp array has been initialized with all zeros. If I found this cell is blocked, then I already know the number of ways to reach the corresponding cells is going to be 0. The same thing will go for the columns. Let us write the same logic for the column as well. Here it will become j comma 0. So this we have done for the column. Now for rest of the matrix we can apply our logic, our recurrence. So let us see how we can apply for the rest of the matrix. So I'm going to use a bottom up approach for rest of the matrix. I can say for int I equals to 1, I less than the number of rows I have, I plus plus. For int j equal to 1, j less than the number of columns I have, j plus plus. If we see a cell is blocked, we do not need to do anything. If cell is blocked, leave it. Go to the next cell. So if you see that dp of ij is marked as -1, it means the cell is blocked, then we do not need to do anything. Continue. Otherwise, let us say the answer for the current cell is 0 and we will try to figure out what is the answer. And I can check if the previous cell, if dp of I and j minus 1, the cell in the same row but in the previous column, if that was not blocked, it means I can reach through that cell. So I can say dp of ij is going to be equal to dp of I comma j minus 1 percentage mod. And I can check if the cell in the top is not blocked. If dp of I minus 1 j is not equal to -1, it means I can come from the top as well. So dp of ij is going to be equal to dp of ij plus dp of I minus 1 j and whole percentage mod, whole mod and this is our answer. The last check which we have to add in this problem is if the final cell is blocked, then there is no way to reach it, right? So let us check for the final cell. If dp of row -1 and column -1 is equal to -1, it means we cannot reach the final cell. I can say return 0. Otherwise we will return the answer which we have already formed. Return dp of row -1 and column -1. So what I have done here is I will just give a quick recap that if I am standing at a particular cell, let's say this cell is ij, so I check if this cell is not blocked. Yes, it is not blocked. Then I check, can I come from the left for this condition? This cell is I comma j minus 1. Can I enter this cell from the left? Yes, I can enter. So suppose there are 5 ways to reach this cell. I can say to reach this cell there are 5 ways. And then I check if the topmost cell, which is I minus 1 and j, this cell, I minus 1 and j. If this is not blocked, yes, it is not blocked, and number of ways to reach this cell are 7. So I say the answer is going to be 5 plus 7, which is 12. And finally I check if the destination is blocked. If this cell is minus 1, then the number of ways is 0. Otherwise, I already know the answer, which is at dp of row minus 1 and column minus 1. There is a small change here, that it should be row, and that's it. This should be moved outside the for loop. Right. Now let us try to run our code for the sample input and check if it works fine. So let me copy the sample input. And let us see what is the final answer. Yeah, so for this case the answer is 2, and let us submit the code on CodeChef. Alright, so it got accepted. So you can see, using a very basic top-down bottom-up DP approach, we have solved this problem. So this kind of approach is used in many path-based, maze-based problems. So you can know how you can apply this approach. One last thing which I would like to show you, you can also print the entire DP table and you can check what all values have been generated so far. So you just need to have two loops, one for I, one for the rows and one for the columns, and you can see what the DP table is. And let us say I am removing all the obstacles from the sample input, and we will see what the answer is. So you will see it is very similar to the answer we have, very similar to the table we had built, right? So I'm removing all the obstacles. There are 4 rows, 3 columns, and let us see what the output is. So you can see here, so for the first row it is 1 1 1, which we had done so far, and for the corresponding entries you can say it is 2, it is 3, it is again 3, it is 6, and it is again 1 4 and 10, right? So it is similar to the grid we had built in our example here, right? So it is very similar to this grid. This is how exactly the bottom-up DP is working. So I hope you understood this problem and learned something new. Thank you for watching. I will see you in the next tutorial.
Hi everyone, in this video we will discuss this problem gold grid, that is from HackerBlocks. So let's go through the problem statement, and it's going to be a grid based problem. Okay, so it says there is a game field, there is a grid of size n cross n. Each square in the grid has or does not have a gold coin. Okay, so there is going to be a 2D matrix in which some of the cells are going to contain a gold coin. So Cyan has to divide the game field with 3 other friends as follows. He will draw one horizontal line and one vertical line to divide the grid into 4 rectangles. Okay, his friends will choose the four three of the four rectangles, and he will get the last one. Okay, so he wants to divide the field so that he gets the maximum number of gold coins, assuming that his friends will pick the best 3 rectangles. Okay, so let's go through the problem once again. Okay, so what it is given is like this. Yeah. Okay. So you're given something like this. There is a 2D matrix, and you're given the locations where in this matrix the gold coins are present. Okay, so those locations are given to you. Maybe there is a gold coin, 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 and so on. So the task is to divide this field into four parts by making two cuts, one along the columns and one cut along the rows. Okay, and every cut will have certain number of gold coins. For example, the partition created in this part has a one gold coin. Here you have two gold coins, and maybe here you have three gold coins. Okay, and here you have one gold coin. Okay, so what is going to happen, the partition that has minimum number of gold coins, that will be given to Cyan, and his task is to maximize the minimum number of coins he is going to get. Okay, so he want to get the maximum number of gold coins, but once he has made the cuts, he will only get the minimum gold coins that is present in any one partition, any one rectangle. Okay, so that is what he is going to get. So his task is to make a partition such that his minimum is also maximized. So that's the question. Okay, for example, if you have a grid which looks something like this, and if he comes up with this particular partition, and this partition is, I think, the best partition for this example, and he will get at least three coins. So you have to output how many coins he will get. Okay, so let's go to the sample input. In the sample input, it's given, you will be given the grid size, that is 6 cross 6 grid. How many gold coins are there in the grid? 13, and you will be given the 13 coordinates of those gold coins. Okay, so from this information you can construct a 2D matrix. Let's call it as A. So this is the information about the 2D matrix. Okay, this is given to us. Now let's think how we can solve this problem. Okay, so the very first approach that comes in the mind is a brute force one. Okay, so let's talk about what would be a brute force approach. Okay, it's going to be pretty easy. So what you can do in the worst case, you can try out all possible cuts. Okay, so worst case is try out all possible cuts at each location, at each x comma y in the grid. Okay, so you're given this array A, and some positions have 1 while other coordinates have 0. So this kind of a matrix you can construct from the input, and for each x comma y, okay, you try to make a cut. You're saying, okay, at this particular x comma y, I will make a cut, one horizontal and one vertical, and then I will find the sum of the four quadrants I get. Okay, 1 2 3 and 4. So this is 1, this is 2, this is 3, and this is 4. You can find the sum of these quadrants. Okay, so how many cuts you can make? Clearly you can make n square cuts. Okay, and for each cut you can find out the sum of all the four quadrants in n square time. So n square time you can find the sum. So the overall complexity, this approach would be order of n raised to the power 4. And once you know what is the sum of each quadrant, you can say, okay, for all the cuts you will find the minimum of 1 2 3 and 4, and you will maximize it for all the cuts. Okay, so maximum for all cuts. This is what you are going to do, and this is going to be a brute force approach. Now we have to think how we can optimize this particular solution. Okay, let's talk about optimization now. So optimized solution. Okay, so can you think of something that will actually help you to avoid some computations? Okay, so clearly we cannot reduce the number of cuts because we cannot make a random guess this is going to be the best cut. So we cannot directly find out the right cut. So this part we still have to do. We cannot do any such optimization at this point, but we can do some optimization at this point because suppose this is the grid, and let's say you are finding out the sum of this particular rectangle, and maybe little later on you also need the sum of this whole rectangle. Okay, so you can see if you have if you have calculated the sum of white rectangle, and if you want to find the sum of this whole rectangle, you do not need to recompute this sum again and again. Okay, so let's say this is x comma y, this is, let's say, x dash comma y dash. So if you know, if you want to find the sum of this whole rectangle, let's call it as dp of x comma y. So dp of x comma y stores the sum of all elements starting from the corner 0 0 till the corner x comma y, let's say. So this is what dp of x comma y denotes, and clearly it also depends upon dp of x dash and y dash. And if you have already computed this small rectangle, you actually have to reuse it because this is the principle of dp. Okay, so dp says reuse the problems you have computed earlier. Okay, so this leads to an idea of prefix sum. Okay, so we can use something like a prefix sum dp in this case. Okay, and this is going to be in 2D. So we have done some problems on prefix sum in 1D. Suppose you want to find the sum of an array. Okay, sum of, let's say, maybe a segment of the array. So what you generally do, you make a cumulative sum array, and if you want to find the sum of this particular segment, you say, okay, this index is j, if this index is I, and you want to find out this particular sum, you simply say dp of j minus dp of I. This is what we actually do, but this is a 1D case. A similar extension can be applied to the 2D case. Okay, so let us see how we can apply 2D prefix sum dp in this problem. Okay, now suppose this is the grid, and suppose at this point, let's say we are making these cuts at this particular cell, and let's call this cell as x comma y. Okay, let's say this is x comma y, and suppose I want to store dp of xy. I make another matrix, that is dp matrix. It's going to be 2D matrix, and it's going to be of the order n square, and I want to compute what would be the sum of this particular box. Okay, if I want to make this matrix. Okay, so clearly, suppose we know, suppose we have already computed the sum of this box. Okay, let me just draw here. Okay, suppose we already know the sum of this box, so this sum is going to be, what is this cell? Okay, so this is going to be dp of x comma y minus 1. Okay, and suppose we also know the sum of this particular box, and since this box ends at x minus 1 comma y, this sum is going to be dp of x minus 1 comma y. Okay, and what we actually need to do is we also need to subtract this much part. Okay, so this blue part, what is this sum? Okay, so this sum is going to be dp of x minus 1 and y minus 1. So I will subtract this part, dp of x minus 1 y minus 1. Okay, so this recurrence shows me that if I know the answer to my sub problems, let's call this as rectangle 1, this is rectangle 2, and this is rectangle 3. So if I do 1 plus 2 minus 3, I will actually get the sum of elements in this part, plus I have to look what is present at this particular cell. Okay, so plus I will add 1 or I will add 0 if there is a coin, at location xy. So I will add 1 if a coin is present at xy, and I will add 0 if no coin is present at x comma y. So this recurrence actually shows me that I can compute the total number of coins present at each location in order one time. Okay, so total number of coins present from 00 to x comma y at any given cell, okay, at any given xy in order one time, or I can say I can compute this in order n square time for entire matrix. Okay, for entire matrix. Okay, so you have to construct a dp array, and that is going to store a 2D prefix sum, and this is the formula that we have derived for the 2D prefix sum. Okay, so suppose now in any given 2D array, you know how many gold coins are present at this point, up to this particular point. Okay, and now you suppose you make a cut at given x comma y at this particular point. You are interested in finding out the four values. Okay, so let me just draw this again, and let's say at this particular point you are making a cut, so you want to know the value of rectangle 1, rectangle 2, rectangle 3, and you want to know rectangle 4 also. Okay, so how do we compute these four values? Okay, so that is also easy. We can just extend this formula. So rectangle 1, if I talk about what's going to be the number of coins in rectangle 1, so it's going to be dp of x comma y. That's it for this particular xy. Okay, let's say this is xy. What is the number of coins in rectangle 2? Let's say this is a m cross n grid, assuming this is a rectangular grid. So what is the number of coins you will have in rectangle 2? So that is pretty easy. So what do you need to do? You know the number of coins in this whole rectangle. Okay, and if you subtract the number of coins in rectangle 1, you will get the number of coins in second partition. That is going to be dp of this whole rectangle. So this, if I talk about this whole rectangle, this is going to be x is the row number of columns is going to be n, minus this first rectangle. Okay, so that will give me how many coins I have in the second part. So this is going to be minus dp of x comma y. Similarly, I can say the number of rectangles in the third part. Okay, in the third part, so this will be this whole rectangle minus this particular rectangle. Okay, so this is dp of m comma y minus dp of x comma y. Okay, and if I talk about number of rectangles, number of coins in the fourth part, so fourth part is again very simple. So what we need to do, we know how many coins we have in this part. We also know how many coins we have. Okay, so let's see for fourth. Okay, so if I talk about this particular cell, that is dp of m comma n, if I note the total number of coins up to this point, okay, and if I subtract the answer for this part, this part, and this part. Okay, so what I can do is yeah, one way is I can just subtract these three things. Okay, this is 1, this is 2, and this is 3. I can just say to calculate 4, I should know the total number of coins in the entire grid that is ending at this particular x comma y, that's m comma n. So I can say dp of m comma n minus 1, minus 2, and minus 3. Okay, that's pretty simple. Or you can also write it like this: you subtract this, you subtract this, and you add this. That is also fine. Okay, so this is also fine. So yeah, now you know what is the number of gold coins present in each part: 1, 2, 3, and 4. And now the question is very simple: what you will do for every value of xy, okay, that lies in the range 0 to n. Okay, for every xy, what you will do, you will find out an answer that is uh, maximum of your previous answer that you have computed. and that should be minimum of your 1 2 3 and 4, something like this. Okay, and this will give you the final answer for the uh, question. Okay, so the coding part is relatively simple. What you need to do, you need to do it in two steps. Firstly, you need to compute the dp array from the given input array, and secondly you need to compute these four things, and these four things for every value of xy. Okay, and then you will find out what is the maximum of minimum possible rectangle that you can get after making a cut. Okay, so the complexity of this approach would be order of n square, because this for loop will run in order n square time, and this is a order 1 operation, and this will also take order n square time to compute, but it's a pre-computation. Okay, so this is going to be n square plus n square, that is going to be order of n square. Earlier it was n square into n square, that was order of n4. Okay, so I hope you got the idea how to approach this particular problem. Okay, so thanks a lot, see you guys in the next video, and coding part I have left for you, you have to implement it yourself. Hi everyone, in this video we will discuss one problem from Code Forces, and it's a very interesting problem, and it's from the contest 429, and problem is B. Okay, so let me just give you a short summarized version of this problem. So it says you're given a 2D matrix of n rows and m columns, and each element of the matrix Aij denotes the number of calories a person will burn. Okay, so a two person, a boy and a girl, start from two corners of this matrix. So there is a matrix like this, and there are two persons, boy and a girl. The boy starts from the cell 1 comma 1, so this particular first cell is 1 comma 1, so boy is there, and need to reach cell n comma n. So boy wants to reach this particular cell. Okay, by following some path, and the girl cell starts from the cell n comma 1, so the girl is at this point and needs to reach 1 comma n, so the girl wants to reach this particular cell. Okay, and both the boy can move right and down, so a boy can go right and it can go down from any cell. Okay, the girl can move right and up, so a girl is allowed to move right and a girl is allowed to move up. Okay, as they visit a cell, the amount in the cell Aij is added to their total calories burned. Okay, so whatever is the path they will traverse, that is the number of calories they will burn. Okay, and those calories will depend upon the cells they have traversed during their path. Okay, so our goal is to maximize the sum of total calories burnt by both of them under the condition. Okay, so let's say what is the condition, they shall meet at exactly one point. Okay, so it says there should be only one point of intersection, so you cannot have more than one cell that is common in their path, and the cost of this cell shall not be included in either of their total. Okay, so for this particular cell no calories will be added to their total. Okay, so this is what you need to solve. Okay, so I will suggest you take 2 minutes to think about to how to approach this kind of a problem now. Okay, so the first thing that might come to your mind is that if you compute the maximum sum path for boy and girl independently. Okay, so some students might think, okay, let's compute the path for boy and let's compute the path for the girl, and let's subtract the common cell and we will get the maximum calories burned. Okay, so this obviously is a wrong solution, because if you compute this independently, it is possible that you have more cells that are getting intersected in their path. Okay, you might get a path like this. Secondly, suppose even if you get a path in which only one cell is common, maybe by avoiding some other cell you might get a better path. Okay, so that is also possible. Okay, so this is actually a wrong solution, so you can't do it like this. So first thing that we have to actually ensure is the constraint. Okay, so we have to ensure the constraint that both boy and girl meet at exactly one point. Okay, so boy and girl meet at only, rather I should use the word intersect, because uh, it is also possible that they intersect but the point is um, okay, so it's possible that they intersect, they cross that point at a different time step. Okay, so let's say a boy goes through that point at t equal to 4, girl goes through that point at t equal to 6. So it is not exact a meeting, but this is an intersection in their path. Okay, so boy and girl intersect at one point. So this is the thing that we actually need to ensure first. So let us see how we can actually ensure this constraint. Suppose the cell is like this, and the boy can enter this cell from the top, or boy can enter this cell from the left. Okay, suppose this is the point of intersection. Okay, and we also know a girl can enter this particular cell from the bottom. Okay, and a girl can exit this cell towards right, and a girl can exit this cell towards top also. Okay, so what I will do, I'll first consider the case in which boy is entering from the top. Okay, so girl goes out from this. Also boy will go out, can go out in this direction, and boy can also go out in this direction. Okay, so we have to choose a direction such that intersection does not happen. Okay, so let us assume the boy uh, comes from the top. Okay, and now a girl can come either from the left, or the girl can come either from the bottom. Okay, so it means if the boy is coming from the top, girl is coming from the left, or girl is coming from the bottom, a girl will have two options. Okay, so if the girl that comes from the bottom, she cannot move towards the top, because that cell will be again a cell that is getting intersected. So girl from the bottom cannot go towards the topmost direction. Okay, or let's say the other option is a girl goes in the right direction. Okay, a girl goes like this. So if a girl goes like this, that comes from the bottom. Okay, so again, so that would mean oh, all right. So what I'm saying is, okay, let's consider this case in which boy is coming from the top, and let's say girl is coming from the bottom. So I'm saying that this kind of a case won't be possible, because if the girl comes from the bottom and it goes in the right direction, then a boy can neither go in right, because if he goes right there will be an intersection, and if he goes down then again it will be, this cell will be a intersection, and hence we cannot have more than one intersection. So such a case won't be possible where boy and girl are coming from the same direction. Okay, so like boy coming from the top and girl coming from the bottom, this won't be a valid case. Similarly, boy coming from the left and maybe, yeah. Okay, let me come to other case. Okay, so what is the only possibility that is left is, uh, if a boy is coming from the top, there is no option for the girl to come, except the girl must come from the left. So the girl must enter the self from the left. So the girl will enter from this direction, and now the girl that enters from the left cannot go to the top because boy is coming from that cell. So a girl must enter exit towards the right. So this is where the girl should take an exit, and since the girl has already taken an exit in the right, a boy cannot go right, a boy must go in the down direction. So if you are able to ensure this constraint, you will ensure that there is no more than one intersection, and from this point a girl can go uh, to her destination, and boy can also go to his destination, that is towards this particular cell. Okay, so that is one case. So if a boy is coming from the top, he must go down, and if a girl is coming from the left, she must go towards right. Okay, so that is one possible case. A similar case would be if a girl is coming from bottom. Okay, and then let's say the boy cannot come from the top, then boy must enter from the left, and now this girl cannot exit towards right because uh, of the similar reason. Okay, so the girl must exit towards top, and boy must exit towards right. Okay, so this is another case. So these will be the only two cases that you have to handle. Okay, so at any given cell, these are the possible directions in which a boy and a girl can come. Okay, so this is the first case, and this is the second case. So let us now try to find out what is the maximum cost path if we have first as our case. Okay, so we need to find out what is the maximum cost path we can make. Okay, so let me just draw the grid. Okay, so let me say this is the point of intersection, I comma j or x comma y, whatever it is. So let's say in the first case boy is coming from the top. Okay, so that would mean we would need how much, sorry, in this particular box. Okay, we would need to find out what is the maximum calories a boy can burn to reach this point. This you can actually compute using dp. And for the girl, we would require what is the maximum calories she can burn uh, by traversing this path. Okay, so how do you compute this? Okay, so you can make a 2D dp table that shows how much calories it can burn. So let's call this table as dp1, and you can use the same approach that we have discussed in earlier videos. You will take a maximum of mm, the left and the right, whatever direction. Okay, so if you are reaching this point and you are reaching this point, here you have burned 18 calories, here you have burned 22 calories, and here you have 2 calories. So the answer for this cell will be 22. A similar approach you can apply from the this corner to all other cells in the grid. Okay, so starting from this as a source, you apply this approach to all other cells. Okay, so you will get how many calories a girl can burn, but if she wants to reach this particular cell, that is 2. And you also know, once you boy is coming out, it will come out from this particular cell. Okay, so you actually need to find out how many calories he will burn while traversing the third path. And for the girl, you know, it will come out of this cell, how many calories it will burn while traversing the path 4. Okay, so what you need to do, you need to build 4 dp tables: dp1, dp2, dp3, and dp4. Okay, so each dp table will store how many calories are burnt while traversing from this as a source to any given cell, and dp2 will store from this cell to any other cell in the grid how many calories you will burn. And for dp3, what we can do, instead of taking this as a source, we can say, okay, let's compute how many calories we will burn if we traverse from this cell as a source to all other cells in the grid. Okay, so that is what you will compute in dp3. So I'll just reverse the direction of the arrow, and dp4 will compute how many calories you will burn if you start from this particular cell and you reach any other cell in the grid. So this is actually the pre-computation you have to do once. Okay, so the time that you will take to compute this is 4 into n square, that is order of n square. Okay, so you're making 4 tables, and each table is really helpful to know how many calories you will burn. Okay, so once you have these 4 tables, so you can see if for the first case how many calories you will burn in total, that will be dp1 of, okay, that is the calories boy will burn starting from this point to this point. this point is nothing but I minus 1 and j plus dp2 of, okay, from this point to this point. So this point is nothing but I comma j minus 1 plus dp3 of this cell. Okay, so that denotes the total calories you will burn from this point to this point, that is I plus 1 and j plus dp4 of this cell. Okay, so that is I comma j plus 1. Okay, so that will give you the total number of calories for the first option. So this is how you will compute the first option. Similarly, you will also compute the second option. So let us see what will happen in the second option. Okay, you will have a grid. Okay, and let us say this is the intersection point I comma j, and boy will come from the left and it will go in right. So for the boy you need to compute how many calories it will burn from starting to this particular point, and how many calories it will burn for the rest of the path. Okay, so that is uh, actually for this path. Okay, this for this path. Okay, boy enters from the left and it goes right, and for the girl it will be like this: a girl enters from the down and it exits towards the top and this part. Okay, and let's say this cell is I comma j. Okay, so for the second cell it would be like this: it would be uh, dp1 of I comma j minus 1 plus this these calories of the boy, that is dp of I comma j dp2 or dp3. Okay, dp3 of I comma j plus 1 plus the calories of girl, that is this dp2 of I plus 1 and j plus these calories of the girl, that is dp of 4 of I minus 1 and j. Okay, so something like this you will need to compute, and then you will put a for loop for I equals to 2 to n minus 2, for j equal to 2 to n minus 2, for all possible intersection cells. Okay, so all the intersection cells can lie in the middle. For all these paths you will say answer equals to maximum of answer, whatever is your previous answer, and you will put value of 1 and 2. Okay, so you will compute 1 and 2 and you will find the maximum of the answer. Okay, this is what you need to do. So the coding part, I will just give you a quick walkthrough of the code, but you can implement this yourself. Okay, so I have made 4 dp arrays: boy start, boy end, girl start and girl end. So the starting path of the boy, the ending path of the boy, starting part of the girl, ending part of the girl. Okay, so this is actually my dp1, this is my dp3, this is my dp2, and this is my dp4. So firstly I need to pre-compute these matrices. Okay, so this is how we compute. Okay, so the maximum of the two positions. Okay, so if the boy is reaching this position from, let's say, top and from right, so I take a max of, here the calories is x, here the calories is y, so I take max of x comma y plus whatever is the calorie number to what are the calories that he will burn at this particular cell. Similarly for the girl, I compute in this direction, starting from here to any other cell, how many calories the girl will burn. Okay, so that would be for given I comma j, I will be taking maximum of this particular cell, that is I plus 1 and j, and I comma j minus 1, this particular cell. Okay, plus whatever is the calories she will burn at this place. So this is how we can compute dp2. Then dp3. Okay, for dp3 I'm saying, okay, from this point to this point you can make a computation, because um, This point is fixed and all other points can vary when you change the intersection point. So it's going to be like this. I okay, I comma j, so it's like I plus, yeah. So actually I want to compute something like this. Okay, starting from this as a source. So at this cell you can come from uh, this point or this point. So this point is I plus 1 and j, and this point is I comma j plus 1. So you take a max of these two, and similarly for dp4. And finally, to compute the answer, what you need to do, you need to consider all points as the meeting points. Okay, so iterate over all possible meeting points between 2 comma 2 to m minus 1 and n minus 1. And if this point is the meeting point, then what is the calories it will burn? So we have case 1 and we have case 2, and we have discussed the equations for case 1 and 2. And finally answer will be maximum of answer or 1 or 2. Okay, so this I have discussed in the video. So that's all what you need to do to solve this problem. So I hope you got an idea and you would be able to solve this problem now. Thanks a lot. See you guys in the next video.